Alright, hell yeah. So we have material mechanics, and this isn't a starred problem, but man, it just seems for me like it's confusing. But this is an elastoplastic problem, which should just be like hell yeah, because all you're doing is you're just taking something to the absolute max, and like your free body diagrams get easier because you're just, you know what I mean, whatever the strength in the material can take, it's just the absolute max. And so the equations that we're going to be using is like the braking stress, or I mean, this is just called stress, but stress is force over area. Okay, but what I like to teach is like, cool, you've already chosen the area. So now the other two things you can put subscripts on. You know what I mean? You could say, hey, this is the braking strength. You know what I mean? Whatever that would mean is equal to the force brake divided by area. Or you could say sigma. This is also the Greek term sigma. So sometimes you'll see sigma. Sometimes you'll say strength. I like to say, sorry, stress. But I do like to say strength. So you could say, but I guess we'll use stress. You could say the allowable stress is equal to the force allowable divided by the area. The design stress is equal to the force design divided by area. And then like yield stress is force yield divided by area. So all I'm getting at is these are the two terms that can have subscripts. Now the other equation for material mechanics is stretch. I call it stretch, it's strain. But this is change in length divided by length. Again, this is, you've already built something, and then you're analyzing it. So this term, heck, you know, it's just like area; it doesn't change. Now the strain and change in length can get subscripts. You know what I mean? So you could be, you know what I mean, max strain. You know what I mean? Max change in length divided by length. Yield strain, change in length yield, whoops, that's a y, divided by length. Okay, I think we get it. So now we're going to move on to this problem. And I always like, how do you simplify things? You know what I mean? How can you make this problem simpler? Alright, hell yeah. We might want to like kind of read the problem. So we have a diameter of a 1/2 inch. So that's kind of what we're working with. And it doesn't specify what the material is, but 36,000 pounds per square inch, that's 36 KSI. Well, that can be the yield stress of steel. So we're probably dealing with steel. If it doesn't say so, we just kind of know that by the yield stress. Sometimes the yield stress of steel, I'll be using it sometimes at 58,000 pounds per inch squared. But this is and this term's in PSI. Cool. All right, so so we kind of already know this. So we know our stress, yield stress. All right, so now we're going to, but this problem says, hey, we're gonna pre-stress this steel bar with 10,000 pounds per square inch. You know what I mean? So whatever force is required to have the pressure of every molecule in here get to 10,000 pounds per square inch. Well, that's what we're pre-stressing it. Then the problem says now we're going to apply a load P this way, and we want to know what's the max load before it turns plastic. And the second you get a load that makes everything plastic, well, you know, if you try to go higher than that, then everything's just going to, you know, permanently, I mean, just keep Play-Dohing out until it breaks. But if you pass the plastic load, then heck yeah, there's no stopping. It's just going to, like pulling taffy until it breaks. But you can go up to that plastic load, and that's where at least something is preventing it from turning into a total catastrophe. All right, so that's what we're given, and you know what I mean. So I had a hard time, you know, me trying to get to the answer, and I was thinking just like, well, let's just get to the answer because, well, no, we need to kind of explain this. So the way that I first, you know, thought of like, okay, I think I can get it. Well, no, that was a problem similar, but not an elastoplastic. So I mean, I guess here it is. I'm just gonna say it outright. So, and it's interesting where, yeah, we'll get to the second part, but I mean, it's anytime you're working with the plastic limit, you know, and working with elastoplastics, technically it should be easy because you're just taking things to the absolute limit, and the absolute limit in this case, there's two ways you can look at this. You know, you could say, hey, this is the absolute force, and this is the absolute pressure in psi of all the molecules. I think psi is kind of a harder term to maybe grasp. Be like, well, what force does that take? Well, that's the relationship right there. Just divide force by area, and you got that. But with plastic loads, it says, hey, the psi can only reach sigma y of 36,000 ksi. But I guess this problem needs to be simplified just a little bit. You know what I mean? So what I'm going to do is going to simplify this problem and just do half a bar. And sorry for being so slow to get here. But if I just have half a bar and then put a load P on and say, hey, I can't go over this, so what's the P going to be? Well, if I know the stress max is 36,000, and I want to find the force, I just rearrange this equation, bring the A upstairs, and I'm going to say the force to yield is the yield stress times the area. And now we're just easy money. We're 36,000 pounds per inch squared times pi divided by 4 times 0.6 inches squared. That's going to be the area of this. So we can just do that. We're going to get 36,000 pi divided by 4 times 0.6 squared. Cool, and we get and also we get 100, well, sorry, 100, oh geez, I can't read numbers. It's just 10,179. And that's going to be pounds, or we're going to do 3 decimal places. We're going to be 10.2 K pounds? How the hell do you say that? KLB? I don't even know. KLB? Sounds like a treat you'd get at McDonald's. I have no idea. Okay, so that's totally wrong. I'm not Kips? Oh yeah, hell yeah. No one uses Kips. That sounds like a snack you get at the dollar store. All right, cool. Kips. And I don't even think you spell it like that. For the love of God, let's just do it like that. But yeah, I think it's Kips. All right, so now we simplified the problem into that. But check this out. Now let's say we have a bar over here. So this was in compression, cool. And the cool thing about steel is same as in compression is tension. But now we're going to take the bar over here, and then we're going to reef on it this way, and then pull it. And then now how much can we put it? Well, it's the same friggin' equation because yeah. And I guess this is a good place to pause because this, you know, this term for strength, you know what I mean, can also be tensile strength, you know what I mean? It can be compressive strength. The only thing it's not is it's not shear, you know what I mean? It's just normal to the direction. That's this whole chapter. We're just doing normal loads to, we're not doing any shear loads, you know, in this section. Okay, so and it just happens to for steel that its tensile strength is equal to the compressive strength. So the yield tensile strength is equal to the yield compressive strength. I don't know. So you just know. I think that's the take-home point. Is like, yeah, these two terms are what can get like whatever you call them. You know, just labels. Anyway, okay, so let's get to it. So the yield stress of this bar will be the force to yield this bar will be the yield stress times the area. It's same thing. I'm not even going to write it, but it's 10,179 pounds. Now, Is it obvious? It wasn't to me that when you put a load on this one that you're stretching this one. So the second you want to put a load on this one, well, this one's trying to resist it. You know what I mean? So I mean that's the other way to look at these, is like, hey, just think of them as springs, because that is exactly what they are. And then we're going to compress this spring. And then while we're trying to compress this, we have to lengthen this spring. And so the change in length of this spring is kind of equal to the reduction of length in this spring. So that's where this problem, maybe get some more time. All right, hell yeah. But I guess my message is, hey, you got two ways to determine when crap breaks. One is, I call this like the scale. It's like the strength. It's poundage. You know what I mean? You can put a pound gauge on something, measure it with a scale. This one is visual, or it's like the ruler. You're measuring a distinct change in length. And once you measure that change in length, let's say the max change in length, well, now you know you're at the max breaking. So these two are synonymous. Max change in length would be sigma max is equal to force max divided by area. So there's two identical ways to figure out when crap breaks. That's the take-home point of material mechanics, especially at the very beginning, and that's the whole point of material mechanics. You have a relationship between, throw a scale on it and then watch it elongate. And that's why any problem, you should be able to get an answer two ways. One, by looking at the scale and then the PSI inside the bar, and then the other thing is just, hey, checking out the change in length. Now for this problem, they don't care. That's why it's just like, I think it would be better for some of these engineering problems to allow you to do it, every problem, especially in the first chapter, do it both ways. You know what I mean? Because it should say here that there's a yield strain. And I think, let's do this. You know what I mean? I'm going to say this is 1 meter and this is 1 meter. And I'm going to kind of combine videos. But let's just get to the end. I mean, the answer at the end of the day was just both these together. It's just twice that. So, I mean, if that's what you came for, it's going to be 10.2 kips. How the hell do you write kips? Is it just K? For the love of God, I have no idea. But it's going to be 20.4. You know what I mean? 10.2 plus 10.2 kips is 20.4 kips. Man, I'm going to have to look that crap up. Alright, but it's 20,400 pounds. That's the answer in the back of the book. Now, we can do B and you can get on with your life. How is the plastic load, how does that change if the initial stress is doubled to 20 KSI? So now we're going to, kind of stretch the spring. So basically you just have this as your spring, and now we're going to say, hey, now I'm going to stretch the spring to out here, and now I'm going to take this point P, and so this string is already stretched. So like when I put the load P right here and start to stretch, maybe I can only stretch it to like right there before this is like, oh hell no. You know what I mean? And that's the whole point about plastic loads. You get to the point where it's just like the bar goes, oh hell no, and that's when it hits this plastic limit. So if it doesn't hit it, and then you can pull on P just a little bit more, and then when you let go of P, every molecule in the bar will go back to its original position. That's this elastic curve. I'm not really going to get into it in this video too much because I kind of want to make faster videos. We talk about it in other videos. But hell yeah, what we're doing is we're taking it past the plastic load, and it can't take any more force. You know what I mean? So this is the yield stress, and yield stress is force divided by area. Area is given, so this is basically also synonymous, or it's proportional to the force, and yeah, you just can't get any more force out of it. So so hell yeah. So let's say we do take this change in length to there. Well, what the hell did we do to this spring? I mean, now this spring, once we lengthen this spring a little bit, sure, this spring looks a little bit more like normal. Okay, cool. It's just like normal, but on the other end of the spectrum, like in compression, we can make this spring look like that before crap hits the fan. So now we can take this, we can maybe change this length by that much now, and now this spring will look like that. And that's when, that's the limit on compression. But while we're lengthening it this extra, this spring is like, hey, I give up. You know what I mean? I can still hold 10,200 pounds, but no more. You know what I mean? So, so at the end of the day, that's why plastic limit problems are easy, because you're just like, yeah, okay, now I see that obviously if this thing's stretched, pre-stressed by stretching it, yeah, you can't put very much load this way. That member is already stretched out, so it's going to hit its plastic load real fast. But this problem says, you know, for the change in length aspect, it's like, who cares? We don't care about where that happens. We just know it's going to happen. Because the other aspect about this distance is hella small. This is like 2 millimeters. If we had a 1 meter bar of steel, you could only change its length by 2 millimeters, and then back off, and every molecule goes back to the same position. But you can plastically load it up to 5%, which would be 50 millimeters before crap hits the fan. Okay, so that's why, you know, just the fact that this bar lengthens significantly doesn't really matter. It can still hold that 10,200 pounds while it's doing that. And then this bar, you know, it's kind of two separate bars now. So this bar is now compressing, and it can only hold 10,200 pounds, because it can only get a PSI in all the molecules of 36. And we've just shown that force divided by area is the PSI. So at the end of the day, it doesn't matter. That's answering question 2. It doesn't matter if you stretch this, you know, if you pre-stress it to 20K. You know what I mean? I think the question C should be, let's F this thing up. Let's stress it to 36 KSI, just right at the limit. You know what I mean? We're almost going to turn this thing plastic. Any more force and this thing is just going to turn into Play-Doh and break. But we're not going to do that. So we're going to take it right up to that limit, and then rigidly put it between the two walls. I'm not going to grab no sheet paper, but this one's good for visual. And now what? Well, shoot, if you put 1 pound of force this direction, you just messed up this side. It's like, I give up, because it's already stressed out. I mean, it's already at its limit. So you just put 1 pound of force in this, and this already went plastic. This part, but this part's just like, thank God. You know what I mean? Because its spring was like this, and now you're just starting to compress this spring. So this side's like, oh, hell yeah, thanks, man. And you can do that until this, the pressure in this side will reach that 36 KSI. And in compression, see, if you stretch this thing to 36 KSI in tension, 36,000 PSI, while you're putting that 1 pound on this side, this side is still in hella tension. So you have to put 10,200 pounds just for this side not to be in tension no more. And once you put 10,000 pounds on this side, it's like, thank you. And now it's neutral. And now you can put another 10,200 to compress the hell out of it and then make it go plastic. All the while, this thing was plastic from the beginning, but it's a really good thing to know. Is just like, hell yeah, this plastic limit starts at 2 millimeters change in length, but, you know, steel, you know, can a meter of steel or 1 unit of steel can get, what's the ratio, 2 to 50? 0.2% compared to 0.05%. What is the ratio on that? I mean, no. This is 0.2% and this is 5%. So 5 divided by 0.2, yeah, it's 25. Well, obviously, 2 times 25. So, I mean, you can stretch it 25 times, you know, that length. So anyway, so that's a pretty good place to maybe stop. And hell yeah, we kind of learned. Yeah, I think we did. We learned from the spring aspect why. You know, and the whole point was, hell yeah, yield stress. Every molecule in here can only take so much PSI. And And if you pull on something in the middle, one part's in tension up to this limit, and then the other part can go to compression to that limit. So that's why it's twice. You know what I mean? It's like twice. It's both of these added together. All right, hell yeah. I don't think we learned anything, but I had a lot of fun with this one. You know what I mean? I think that's all anyone wants, and I can give you that. I can give you that. All right, so thanks for joining me, and guess what? That's a video.